APPC Calculus class. This video is about improper integrals. But before we jump into the improper integrals, we must know what is the end behavior of some major functions. So for example, e to the x, you have to have some idea what is e to the x looks like when x goes to infinity and when x goes to negative infinity. So for example, e to the x is exponential growth function, and we can see that x goes to infinity, it goes to infinity, negative infinity is a 0. So you can pause the video for a few minutes and try to answer this, try to sketch the graph of all of this and check what is their end behavior. Now I'm going to go over here, log graph ln x. You must have a clear idea what is ln x looks like. So ln x always have a vertical asymptote at x equal to 0. And when x goes to infinity, it goes to infinity. X goes to 0 from the positive side, it goes to negative infinity. Now negative e to the x is a reflection over the x-axis, and you can see that the graph is reflected. So the x goes to infinity, it goes to negative infinity, x goes to negative infinity, it becomes 0. E to the negative x is an exponential decay graph. Another one is a 1 over x. This is a rational function. You must have a clear idea what the graph look like. The reason is we are going to see the integration near the 0, which means between 0 and 1, how much is this area, or 1 to infinity, how much is this area. So you can see that this kind of problems, we are going to do it, which means the one of the bound is infinity, and here there is a vertical asymptote. So we need to know how this graph look like. Now, one more important function is a tangent inverse. In pre-calculus, we learned how the tangent inverse graph look like. It is a sideways graph. It has a 2 horizontal asymptote, positive pi over 2 and negative pi over 2. So we are going to look at the area questions, and we are going to use the inverse trig function. So we'll talk about this while I introduce the lesson on the next page. Okay, so improper integrals. Why we use the word improper? Improper means their bounds are not real numbers. In other words, we are going to look at the area near the horizontal and vertical asymptotes. So you can say infinite limits of integration, which means either positive infinity or negative infinity. It could be horizontal asymptote or it could be vertical asymptote. So before we start about doing work, kind of an exploration. So without, it says use a calculator, but I'm going to give the answer. Like what is 1 over x function look like? And we are going to see the area from 1 to several different numbers. And we are going to make a decision that it's this area as x goes to infinity converge or diverge. Converging and diverging are the buzzwords you will hear so many times in Unit 10 as well. So here is a 3 numbers. 1 to 100, 1 over x, which means if I find this area 1 to 100, I get 4.6052. If I increase to 1000, I'm adding just a few numbers, 6.9077. And if I make my upper bound is a very, very large number, it is 13.855. So what's our conclusion here is, what if I go to infinity? Would I get an answer? So no. Even if these numbers are slowly increasing, but they are increasing. So we say that this integral 1 to infinity 1 over x dx diverge. Now here in this case, we took the help of calculator and we say that it diverge. But on the next page, we are going to actually evaluate and we see how this integral diverge. So now another scenario is, let's take a look at another function. which is also decreasing, e to the negative x. And if I put these numbers, this is a function look like exponential decay. And again, if I find the area from 1 to 100, calculator will give you 0.3678. If I do 1 through 1000, I have a very similar looking answer. And if I do 1 to 100,000 or even a million, very, very large number, I have an identical number. So what can we say about if it is 1 through infinity? That means no matter what is my upper bound, you will have a same number. And we can say that this integral converge. Converge means no matter what my bound is, I will have a same answer. So now let's think about for a minute that how come both are similar looking graph, both are decreasing graph and similar answer, similar questions, how come one area diverge and one converge? So question here is how can you have unbounded region where one has a finite area and one has infinite area? So it's a very interesting question. This is you have to understand the family of functions. 1 over x is a decreasing function, rational function, which decreases at a steady rate. You can say that the rate means decreasing is this distance is the same as this distance. So it is diverging. It is a very slow function, slowly coming down. Whereas e to the negative x is exponential decay function. When it increases very fast. But when it decreases very fast. If it comes down fast, that means area is converging to 1 over e. So have a clear idea again who is converging, who is diverging, and why. So these are the introduction of uh, improper integrals. We will have to do this without calculator. But what is the definition of improper integrals? So integrals where one of the bound is infinity, whether it's a positive infinity or negative infinity or the both sides, are called improper integrals because one of the three reasons. The reasons are either they have infinite interval of integration, they have discontinuity. Sometimes there is a vertical asymptote in between. So there is a discontinuity on the interior of the interval of integration. So for example, let's take a look at this one. 1 over x square, negative 3 to 3. Now, do you have any idea what is 1 over x square look like? 1 over x square is a even function. It looks like this. Now, negative 3 to 3, let me show you the better picture. Negative 3 to 3. There is a vertical asymptote in between. So none of the bounds are infinite, but this is still improper integral. So vertical asymptote questions are very difficult to, not difficult, but not that easy to identify why they are improper integrals. You must look for where the function is not continuous. If it is not continuous within this bound, that means it is an improper integral. And one of our job is to find this area. So in fact, these past AP questions where what this answer is it converging? Is it diverging? And how do we evaluate? So let's find out on the next page, how do we evaluate improper integrals without calculator? Okay, so here we have a formal notes. They are evaluated by rewriting. Okay, so first thing, you must rewrite as a proper integral. Proper integral, you make them using limits. This is very important step. You have to make them proper before you apply any kind of calculus rules. How do we make improper? How do we make it proper? You have to use the limits. Improper integrals that equals to finite value is said to converge. And if it does not have a number, then we call it diverge. Improper integrals within infinite intervals are easy to spot by looking for infinity bounds or inside. Basically, you look for horizontal and vertical asymptote. Okay, so let's take a look at this notes in the box here is how do we make them proper. So if you have a to infinity f of x dx, then leave the lower bound a as it is, pick a variable b or c or anything, and you make limit statement here that b goes to infinity and make that upper bound as a b. Now, why we have to do this? Why can't we write infinity and evaluate the integral? All those calculus rules and fundamental theorem of calculus and all those, they are only valid for real numbers. Infinity is not a real number. So we have to place a variable for infinity, do all the calculus, and at the end, bring the limit statement back to see if it converge or diverge. So here is a negative infinity to b, then you can choose, keep the upper bound b as it is, and choose another letter a as a goes to negative infinity. These are considered very simple, easiest kind of examples where you just have to use a limit statement and do the calculus. Now, sometimes you have upper bound and lower bound, both of them are infinity, negative infinity to positive infinity. Then you must split this into two interval, negative infinity to c, c to infinity, and then use the help of 1 and 2 to evaluate two integrals. Yes, you have to evaluate two integrals separately. Now, good news is if one of the integral diverge, you don't have to do the other one. So let's read this carefully. For improper integral, if in the third case, if left one diverge or a right one diverge, both of the whole entire integral diverge. So basically, if one of them is a party pooper, you stop working on the right one. You don't even have to do the right side. You can say this integral diverge, therefore this one diverge. We are going to look at all of them. Now, again, today is a day 1 of improper integrals. Day 2, we are going to look at the vertical asymptote. So these are the examples here where we talked about how 1 over x, 1 to infinity diverge. So unfortunately, I will have to reveal all of them, but let me show you one at a time here. So choose the variable b. So limit b goes to infinity, 1 to b, 1 over x dx. This is your normal integral. Now, what is the antiderivative of 1 over x is ln x. So then you rewrite ln x ftc 1 to b, limit b goes to infinity. You can write it once and you have to copy it down. Now, another reason here we cannot write infinity here. Do not write infinity here. That is a wrong, because fundamental theorem of calculus cannot be applied to something which does not exist. Infinity does not exist. Do not write infinity here. That's the whole reason. If something does not exist, we can't apply FTC. So it's pretty much straightforward. Now, once you use a limit statement, ln x, ln b minus ln 1. Okay. So just focus on this one example here, ln b minus ln 1. Now, we know ln 1 is a 0. And we have to think about this piece from the warm-up. How does log graph look like? Log graph looks like this. B is a variable. X, think about ln x, x goes to infinity. So this is end behavior of a log graph. X goes to infinity. Ln x also goes to infinity. So what will be the final answer? We can say infinity, because this goes to infinity, minus 0, and this integral diverge, which we already looked at on the other side, and we say that this integral diverge, but this was with the help of calculator. Now we are doing this without help of calculator. So it's very interesting, small, cute, nice integrals. The only difference is the upper bound is infinity. So if you pay attention to the pattern, you will come up to some conclusion. So 1 over x is diverging, we got it. Now what if my power is a little bit higher than 1? You see, notice here power is 1. So 3 half, let's say. Now remember, log rule cannot be applied. Log rule is applied only if power is 1. So this is a normal power rule. Now notice that here, B limit statement, you write it once and you copy it down at the end. So power rule, negative 3 half. So that's a negative 1 half over negative 1 half. And 1 to infinity. Now, no, this is a wrong thing. Never write infinity there. This is a B. This is my very old notes. I should not be even showing you this part. This is not. Let me fix them. Yeah, this is better. So negative 2 to square root x, which means negative square root 2 over square root. Now square root, no, 2 over infinity is a 0. Remember, b goes to infinities and square root b. So this is a 0 bottom heavy, and 0 plus 2 is a 2. Same thing here, 1 over infinity is a 0. So limit statement, if I bring down the limit statement, and if I say b goes to infinity, you should not be putting that, b goes to infinity. So 1 over infinity is a 0, so answer is converge. So do you notice that these are all converging, except this? So what do you notice here? Interesting is power is 1, power is increasing, increasing. So you have to come up with the pattern. What is a pattern here? So exponent is greater than 1 in the denominator. These are all 1 over something, which is converging. So P is greater than 1, converge. This is going to be a multiple choice questions, and you have to know what values of P. And you don't want to have a time to evaluate the whole integral. You can just say this is a greater than 1. That means if I'm looking at the horizontal asymptote, then integral converge. So let's take a look at the other side here. Typical multiple choice question, something like this. You don't have to memorize this part. You just have to know that P greater than 1 converge, P less than or equal to 1 diverge. We are going to use this again in a unit 10. This is again unit 10. This is again coming back in unit 10. It will be much easier in unit 10 once we know how to do this here. And sorry. I clicked something. I apologize. Let's come back to. Just have patience with me.